So, over the last couple episodes, we built two different ways to hold a sequence of values. There's the array, one solid block of slots, all sitting next to each other, and the linked list, a chain of little nodes, each one pointing to the next. Today, though, we're not building a new container. Today, we just add a rule. And here's the thing. Two of the most useful structures in all of programming aren't really about where the data lives at all. They're about one simple question. Which value are you allowed to grab next? A stack only lets you grab the most recent thing you added. A queue only lets you grab the oldest. Last in, first out versus first in, first out. And honestly, that one little difference is the whole episode. Two simple rules, sitting right on top of the structures you already know. Let's pull them apart. Okay, a stack. Think of a pile of plates. You add a plate to the top, you take one off the top, and that plate way down at the bottom? That's the last one you're ever gonna reach. Adding a value, we call that a push. The new one just drops right onto the top of the pile. Push again, and it lands on top of that one. And notice what doesn't happen here. Nothing underneath ever moves. We're only ever touching the top. Taking one off, that's a pop. The top value lifts off, comes back to us, and just like that, it's gone. And if you just want to look at the top without taking it, that's called a peek. But careful, because these two are different. A pop removes it and hands it back. A peek only looks. The item stays right where it is. And every single one of these push, pop, peek only ever touches the top. Doesn't matter if the pile is 5 boxes tall or 5 million. The work is exactly the same. All of it. O of 1. And this right here is what last in, first out actually means. The last plate you set down is the very first one you pick back up. The order isn't some side effect, it's the entire point of a stack. Couple of things to watch out for. Pop an empty stack and, well, there's nothing to give back. We call that underflow. And if your stack lives on a fixed size array and you push onto a full one, no room left. That's overflow. So good code always checks before it reaches. Honestly, the biggest stack you use every single day is the call stack. Every time one function calls another, a new frame gets pushed on. It holds that function's variables plus a little note about where to come back to. And when a function finishes, its frame just pops right off. The most recent call always wraps up first. That right there is LIFO. But if a function keeps calling itself forever, those frames just pile up and up until there's no room left. That's the famous Stack Overflow. And yeah, that website you live on, named after this exact error. Undo is a stack too. Every action you take gets pushed on. Hit undo, and the most recent one pops off and gets reversed. And redo? That's just a second stack, sitting there, catching whatever you undid. Stacks even power search. Say you're exploring a maze, going as deep as you can, then backing up whenever you hit a dead end. That's depth-first search, and the stack is what remembers exactly where to back up to. Hold on to that thought. We'll need it later. A queue? That's just a line at the checkout. You join at the back, you get served from the front, and absolutely no cutting. Simple as that. Adding someone on, that's called an enqueue. The new value just joins up at the back of the line. Taking someone off, that's a dequeue, and it always pulls from the front. Whoever's been waiting the longest, they're up first. Now here's the trick that makes this whole thing fast. When the front leaves, the rest of the line does not shuffle forward. We just slide the front marker over by 1. Nobody else has to move an inch. So enqueue only ever touches the back, dequeue only touches the front, and neither one bothers the middle at all. Both of them. O of 1. First in, first out. The order you show up is the order you leave. Oh, and watch the vocabulary here. It's enqueue and dequeue, front and back. Not push, pop, and top. Same kind of idea as a stack, just from the opposite end. So where does a stack or a queue actually live? Remember, these are just rules. We can lay them on top of an array or on top of a linked list. Both work. Each one's got a little catch worth knowing about. A stack on an array is the easy one. You keep a single index called top. Push writes there and bumps it up. Pop reads and bumps it down. All the actions at the end, so nothing ever shifts. It's just like appending to an array. And if it fills up, we just grow it, like a dynamic array. Grab a bigger block, copy over once, amortized O of 1. A stack on a linked list is just as clean. Push and pop both happen right at the head. Point the new node at the old head, slide head over, done. One pointer, and no capacity limit, ever. The queue, though, that's where it gets interesting. On an array, we keep a front index and a back index, but every dequeue marches front forward and just abandons the slot behind it, so the whole queue slowly drifts to the right, leaving this dead space at the start. Eventually, back hits the end and reports that it's full, even though there's all these empty slots sitting wasted at the front, and sliding everything back to the left to reclaim them. That's O of n, the exact cost we're trying to dodge here. But the fix? It's beautiful. When back runs off the end, we just let it wrap around to the front, into the slots we already freed up. Back just jumps right back to slot 0. The next index is just index plus 1, mod capacity, one line of math, nothing wasted, and still O of 1. It's easiest to see if you stop drawing the array as a line and bend it into a ring instead. Now there's no start and no end. Front and back just chase each other around and around. And this is what we call a circular buffer. On the ring, enqueue and dequeue are still just one step each. No drifting, no wasted space, no shifting, ever. And on a linked list, dequeue from the head is easy, but to enqueue at the back without walking the whole list, you keep a second pointer, a tail. So a stack needs one pointer, a queue needs 2, head and tail. The structure itself decides which end does the work. Okay, let's bring it all home. A stack is last in, first out. You only touch the top with push, pop, and peek. A queue is first in, first out. In at the back with enqueue, out at the front with dequeue. And every single one of those operations, O of 1. You'll spot stacks behind the call stack, behind undo, behind depth first search, and queues behind schedulers, buffers, and breadth first search. In fact, the only difference between those two searches is whether your to-do pile is a stack or a queue. Swap the container, and you've changed the entire algorithm. And remember the whole thesis here. Neither one is new storage. They're just rules, layered on the structures you already built. An array with a circular buffer so nothing's wasted, or a linked list with a tail pointer to keep it O of 1. Episodes 1 and 2 put to work. Next time, we take these pieces and let them branch. One value pointing to 2, then 4, then more. A structure that grows downward and outward. The tree. Thanks for hanging out with Code for Code. If stacks and queues finally clicked for you, stick around. There's a whole lot more to build. I'll see you in the next one.